All right, so let's take a look at this problem. We started with the first compound, this ester here, and we found out that the red protons, the methyl protons, are not split by any other protons, and so we would get a singlet for those. Did anybody figure out what kind of splitting we would observe, if any, for the blue protons? Would that give us a singlet, doublet, triplet, quartet? Anybody? And it's not a trick question. Did those protons have any neighbors? Exactly. We would get a singlet, right? Because n plus 1 would be equal to 0 plus 1. And so we get 1. And so we would get a singlet for those methylene protons, right? They're chemically equivalent. They're homotopic. And what else? Yeah, sorry, they're enantiotopic. My mistake. But they're still chemically equivalent. And if we look at their neighbors, right, they have no neighboring protons if we follow 2 or 3 bonds. So if we went 1, 2, 3, right, there's no protons here. 1, 2, 3, no protons there. So, right, so it has no neighbors. And so we get a singlet for those 2 protons. What about the black one here? Could anybody tell me what kind of splitting I get for this one? Would I get a singlet, doublet, triplet, quartet? If I used the n plus 1 rule for this guy? Anybody? How many neighbors? Well, this one has a total of, right, there's 1, 2, 3, 4, 5, 6 neighbors, right? There's free rotation around this bond. And so those 2 methyl groups, all 6 of those protons are chemically equivalent. So we have n plus 1, which is going to be equal to 6 plus 1, which gives us 7. And so we would see a septet for that methine proton. And then for all of these protons, so I'll use purple, I guess. Yeah. So for these ones here, right, there's 6 protons there, but they're all chemically equivalent. And if I do n plus 1, well, they only have one neighbor, right? This guy here. So I have 1 plus 1. And so those would give me a doublet. All right. So the red ones give you a singlet. The blue ones give you a singlet. The purple one gives you a septet because it's split by 6 protons. And then the green ones, those are all chemically equivalent. They're only split by 1. And so we get a doublet. All right. For this one here, okay, anybody get a multiplicity for the red protons? Again, it wouldn't matter if it's this one or this one, they're chemically equivalent. But if I use n plus 1, could anybody tell me how many neighbors do the red protons have? Could anybody tell me that? How many protons are neighboring the 3 protons, the 3 red protons, the ones inside the red circle? 2, exactly. So if I have 2 plus 1, that gives me 3. And so for these ones, I'm going to get a triplet. Good. What about the blue protons? How many neighbors do they have? If I do n plus 1, how many neighbors? How many neighbors for these 2 protons? 3, exactly. So I have 3 plus 1, which gives me 4. And so I'm going to see a quartet for these 2 protons. What about the methine here? I'll use my green pen. So for the methine, if I do n plus 1, how many neighbors does the methine have? Exactly, 3. So I get 3 plus 1, which equals 4. So the methine's going to give me a quartet. And then what about the black protons? How many neighbors do they have? N plus 1. One neighbor. There you go. 1 plus 1, which equals 2. And so I'm going to get a doublet for those, or for those 3 protons. Again, here for this one, I'm going to get a triplet. And then for this one, I'm going to get a doublet. Quartet. My mistake. Quartet. That old quartet of mine. Okay, so now what we're going to do is we're going to flip it around the other way, and we're going to actually look at some splitting, and we're going to see if we can recognize an ethyl, isopropyl, or tert-butyl group. So remember, an ethyl group, right? We have CH3, I'll do it like this, CH2, CH3. And for the CH3 group, we're going to see a triplet that integrates for 3 protons. And for the methylene, we're going to see a quartet that integrates for 2 protons. Then for our tert-butyl group, so for tert-butyl, we have 9 protons that are all chemically equivalent, and they're not split by anything. And so if we see a singlet, so I'll just write here, singlet that integrates for 9 protons, that's going to be a tert-butyl. And the last one is the isopropyl. So if I have something that looks like this, okay, that's an isopropyl group. So I didn't write the name here, isopropyl. Okay, so for the 6 protons, I see a doublet because they're only split by 1 proton. So I see a doublet that integrates for 6 protons. And then for the methine, I see a septet that integrates for 1 proton. Okay, so let's take a look at 15.17a. This one here, does anybody recognize anything in here? In A, do you see an ethyl, tert-butyl, or isopropyl? In A. Yeah, there's an isopropyl in there, isn't there? Thanks, Rubio. Exactly. So I see an isopropyl. So I have this, and I have these. Good, right? So I have a doublet that integrates for 6. So that's going to be the methyl groups. And then I have a septet. Now, keep in mind, this is an expansion because you can't really see that. But here you see that you have 1, 2, 3, 4, 5, 6, 7. So that's a septet that integrates for 1. Keep in mind that the number on the top, that represents the number of protons. 1 proton, 6 protons, not the splitting. There we go. So an isopropyl for that one. What about in B? Does anybody see anything in B? Anybody recognize anything in B? Yeah, I'd say there's both, right? I'd say there's an isopropyl in there and an ethyl. So if we use color coding, so I'll circle the septet and the doublet and say that is an isopropyl. So we'll say these ones, isopropyl. And then if we circle this one here, so that's a quartet that integrates for 2 and a triplet that integrates for 3. So those 2 would be an ethyl group. Good. And what about the last one? Does anybody recognize anything in the last one? Keep in mind they gave us the integration values at the bottom. So they make you do a bunch of extra work in this one. But if you figure out the relative integrations here, this is 2 protons, 2 protons, 1 proton, and 9 protons is the way that it works out. Yeah, thanks, Hannah. It's a tert-butyl. So you have a singlet that integrates for 9 protons. So this is a tert-butyl. Exactly. There you go. So I don't like to use the word easy in an organic chemistry class. It doesn't really belong here, but I'd say these are the most recognizable of all the alkyl groups, okay? The ethyl, the tert-butyl, and the isopropyl. Okay, so section 15.8, we're going to skip that about drawing NMR spectra, and we're going to go right to section 15.9, which says using proton NMR to distinguish between compounds. If you go back to the very first slide, I mean the title page slide, I went on this 5-minute diatribe about how you could take compounds that would be very difficult for you to distinguish, using infrared spectra or mass spectra, but you could do it with NMR very quickly. So if you take a look at these 3 compounds here, if you tried to distinguish between these 3 using IR or MS, it would be very difficult. It says might be difficult. I would say is going to be difficult. Okay, I don't want to do that at all. But if I ran a proton NMR on these 3 compounds, I could distinguish between them in a matter of seconds, because the compound on the far left has a total of 1, 2, 3 signals. The one in the middle has a total of 1, 2, 3, 4 signals. And then the one on the far right has a total of 1. And then these signals are going to be identical. So it's got 2 signals. So very, very quickly, you can tell the difference between these compounds. So hopefully that gets you excited about NMR. You're like, oh boy, I like this. You know, it's going to be way faster than IRRMS once I get the hang of it. And you're absolutely correct. Okay. So question 15.21 is a great question. I really like questions like this. It just says, how would you use proton NMR to distinguish between these 2 compounds? So if we look at A, okay, you see that there's symmetry in the first compound, or the compound on the left. You can clearly see that there's symmetry here, but here there's no symmetry. Okay, they have the same molecular formula. There's no doubt about that. But one compound has symmetry and the other one has no symmetry. So my question to you is, if we just focus on this compound, the one on the left, could anybody tell me how many signals you would see in the proton NMR for this one? Take a second and look at it. Could anybody tell me how many signals would you see? Not whether it's quartet or doublet or triplet, just how many. Thanks, Isaac. You're absolutely right. So Isaac says for this compound, you only get 3 signals. He's absolutely right, because this methylene and this methylene, remember methylene means a CH2 group, those are chemically equivalent. This aromatic proton and this aromatic proton are chemically equivalent. And then these 2, meaning this one and this one, those are chemically equivalent. So here we get 3 signals. All right, 3 signals. Isaac, I have a much more difficult question. Isaac, or anybody, could you tell me how many signals would you see for this? And go with your gut. There's no symmetry in the entire compound. Could anybody tell me? Yeah, you exactly. You'd see 6. Yeah, you guys did it faster than me. I hadn't even tallied it up. So we'd see a total of 1, 2, right? You can see these 2 methylenes are different. And then all of the aromatic protons. This one, this one, this one, and this one. They're all unique. And so for that guy, we'd see a total of 6 signals. So again, very quickly, you can determine which is which. Now, the next one is a bit tougher, because for both of these compounds, you're going to have 2 signals. Okay, you're going to have a singlet that integrates for 3 protons, and you're going to have a singlet that integrates for 9 protons, right? Because you have a methyl and a tert-butyl. Does anybody have another way? There is a way to distinguish between these. Could anybody tell me what technique we could use to distinguish between these? Even if you can't give me the proper explanation, just a rough explanation. How would I distinguish between these 2? These 2 esters, they both give you 2 signals, 2 singlets, right? What about chemical shift? Okay, the way you're going to distinguish between these is using chemical shift. So if I start with this methyl group over here, the baseline of a methyl was 0.9 parts per million, and it's alpha to this carbonyl. So we're going to add 1. So plus 1.0 gives us a total of 1.9 parts per million. So that means for the compound on the left, we should see a singlet at 1.9 parts per million that integrates for 3 protons. Could anybody tell me what the chemical shift of this methyl group would be? The baseline is 0.9, but how much are we going to add if it's next to the oxygen of an ester? Exactly. Thanks, Arubio. You're going to add 3.0, so we end up with a total of 3.9 parts per million. So that's how you're going to distinguish between them. The compound on the left is going to have a singlet that integrates for 3 protons at 1.9 parts per million. And the compound on the right is going to have a singlet that integrates for 3 protons, but at 3.9 parts per million. I wouldn't really use the tert-butyl groups here. You could, I guess, this one is going to be more de-shielded, okay, than the other one. That would work, but the methyl groups are much easier in this case. All right, the next one. I'll test you guys a little bit. For this compound here, the compound in the blue circle, how many signals would you see? Exactly, you see 2 signals. So for this one here, you see a total of, right, Jenny? You see these ones, and then you'd see these ones. So 2 signals. Whereas this guy here, you're going to see 1, 2, and then you got this one down here at the bottom. So you've got a total of 3 signals for that one. All right, somebody asked me a question about this one here. It says, wouldn't the first one be beta to the carbonyl? No, it's alpha. So remember, this carbon is not the alpha carbon. Okay, this would be the alpha carbon. Okay, when it's a halogen, okay, so if it's an alkyl halide, right? Like let's say you have something like let's say you have something like this. If you have an alkyl halide, right, like this bromine, okay, this is an alpha carbon, this is a beta, this is a gamma, okay? But if it's a carbonyl compound, then this is the alpha, this is the beta, this is the gamma. Does that make sense? Okay, cool. Yeah. And then for the last one, we'll start it with this one. Could anybody tell me how many signals you would see for this compound? And obviously there's symmetry in here. We'll just get some practice on it. For this guy in the red oval. For this one, you'd actually see 3 signals, right? Because you have these 2 protons that are chemically equivalent, you have these 2 protons that are chemically equivalent, and then you have the alcohol proton. So for this guy, you would see 3 signals. 3 signals. And then for the one on over here, I mean, you'd see what? 1, 2, 3. I don't know, where's my black pen? 4, 5. So for this guy, you would see 5 signals. There you go. So now we've covered chemical shift, integration. What else? Chemical shift, integration, and splitting. So we've gone over those. So, you know, that's a lot of information to cover. And sometimes students say, well, how do I sort all of this out? If you go into our class's Canvas shell and you go into the chapter 15 module, there is a document in there that I made a few years ago. So I'm just looking it up myself. And it says a strategy for solving spectral problems, Dion. Okay, now that's just something that I came up with, which might help you for solving combined spectroscopy problems where you have IR and MS and NMR all put together. But if you're just thinking about an NMR only, a proton NMR, this is David Klein's 5-step process, and I think it's great. I think it works really, really well. Step 1, if you have a formula, I would calculate the HDI, okay? If, let's put here, if given a formula, okay? If they gave you a formula, then yes, you can calculate the HDI. Next one is look at the number of signals and integration. If you have, you know, a molecule that's got 8 carbons, but you've only got 1 signal or 2 signals, well, then it's pretty much giveaway that you've got some serious symmetry in there somewhere. What else? Integration, of course, try to do the math as much as you can and figure out, you know, how many relative protons there are for each signal. Analyze each signal and start drawing fragments. Like, let's say you think you have an ethyl. If you think you have an ethyl, I would draw it down. I don't know if you've ever heard the expression, it's not a nice one, but throw up on the page, right? Just write down what you know. Is there an isopropyl? Is there an ethyl? Is there a tert-butyl? Whatever, just aromatic, right? Do you think there's an aromatic ring? There's signals, you know, between 6.5 and 8. Write it down and then start trying to put the pieces together. If you like puzzles, you usually like people that like puzzles like NMR, right? Because you have to kind of put it together. And then once you put it together into some kind of structure, The great thing about NMR is you can always check your work. You can look at the molecule that you proposed and say, does this make any sense? You know, would this give me the right spectrum? And if it's wrong, well, then you start modifying it in some way. And I would say, um, you know, and this is something that I've never seen any of you do, but just when it says a structure, make sure that you obey like the octet rule, you know, and bonding rules. Okay, don't start drawing 6 bonds to an oxygen or something. I'll see all kinds of crazy stuff sometimes. That's got nothing to do with chemistry. So there you go. So that finishes the section on proton NMR. And if you're thinking, well, that took a long time, then I don't feel like doing that much more work for another section. Well, the good news is the section about carbon-13 NMR is a lot shorter, okay? And the reason why is because there's no splitting, or we don't look at any splitting in a carbon-13. The only thing we look at are the number of signals and the chemical shift. But before we do that, let's see if we can propose a structure that is consistent with this NMR spectrum here. I actually kind of forgot that I had stuffed this problem in here. But let's see if we can solve this one as a group, okay? And I'll just kind of walk it through you. And I know it's a little bit slow when I ask questions sometimes, but let's try it. Did anybody calculate the HDI for this compound? I haven't, so I'm going to do it right now. Anybody get an HDI? Yeah. Does anybody have an HDI? I got an HDI of 4 for this compound. And when your HDI is 4 or greater, if it's greater than or equal to, okay, I would say here, if HDI is greater than or equal to 4, I would always guess, I would ask myself, is there an aromatic ring in the compound? And remember that aromatic protons come out between 6.5 to 8 parts per million. And we have, you know, some aromatic protons. So we probably have an aromatic ring in our compound. So I'm going to scribble that down. I'm going to say we probably got an aromatic ring in here, like that. Next thing what we'll do is, could anybody tell me how many signals are there? Based on what we've learned, how many signals are there in this spectrum? How many signals do you see here? I'm not talking about quartets and triplets. I'm talking about how many individual signals do you see in this spectrum? There are 4. Thanks, Jenny. Absolutely, right? There are 4 signals. We have a singlet here. We have a triplet here. We have another triplet here. So I'll just put S for singlet, T for triplet. And then this one here, you can't detect any splitting. This is a multiplet of some sort. So it's very difficult to tell what's going on. The next thing that we should do is, we know there are 10 protons, right? It's H10, okay? So if we divide each one of these by 9.1, what do we get? So if we divide each one of these by 9.1, 9.1, 9.1, and 9.1. Well, I don't even need a calculator. I can kind of see the math here. If you take 45 and divide it by 9, right? Here we're going to get pretty close to 5. Here we're going to get close to 2. Here we're going to get close to 2. And here we're going to get, well, not close to, we're going to get 1. Okay, so that tells us that this is 5 protons. This one is 2 protons. This one is 2 protons. And this one is 1 proton, like that. Okay, cool. So now, if the aromatic ring has 5 protons on it, how many substituents are on the aromatic ring? Could anybody answer that? How many groups are attached to the aromatic ring? If it's got 5 protons, right? There's 5 aromatic protons. How many groups are attached to it? The answer is 1, right? So that means that you've got an aromatic ring that's got 1 thing attached to it. Okay, it's got 1 thing, right? Because there are 1, 2, 3, 4, 5 protons. So that means you've only got 1 substituent on your ring. Now, I noticed that if I go down to the lowest chemical shift, I've got something at 2 that has no splitting, and then I've got an oxygen here. So what are the possibilities? If I have an oxygen and I've already used up my HDI, What are the possible functional groups I could have in this compound that have oxygen? Could anybody tell me that? If I've already used up all the units of unsaturated, an alcohol is one. Okay, it's either alcohol or there's another one that it could be. It's either an alcohol or an ether, right? Because those both possess. It couldn't be an ester, because if it was an ester, you'd have to have an HDI of at least 5, right? Because then you'd have another double bond, right? So we can't have that because we've already used up all the HDI in the aromatic. Now, we've got 2 triplets and a singlet. So if we have something that integrates for 2 protons, right? 2 protons, and 1 proton, okay? How do I get a triplet that integrates for 2 protons? The only way I can have that is to have a CH2 group, okay, split by another CH2 group. CH2 group, like this, right? Because the one in black has 2 neighbors, so it's going to give me a triplet. And then the one in red has 2 neighbors, so it's going to give me a triplet. So I get 2 triplets, okay, that both integrate for 2 protons, but then they both have to be attached to groups that do not have neighboring protons. So what are the possibilities at this point? The only possibility is it can't be an ether, because there's no way for me to put an oxygen here and then an aromatic ring, right? I can't do that because then I have nothing left to put over here. So what does that mean? What that means is that I'm going to have an alcohol on one side. So I'm going to have CH2, CH2, and I'm going to have an alcohol on one side, and then I have my aromatic ring on the other side, like that. So there's the compound. It must be this compound here. Now, in terms of annotation, how do you annotate an NMR spectrum properly? The way you do it is this. You start on the far right with the lowest chemical shift, and you start using the alphabet, A, B, C, D, E, F, G, et cetera, for every signal. So here we have A, B, C, D starting on the far right. And so what you do is you put that letter by the proton. So HA must be the singlet, right? Comes from the alcohol. Then between B and C, which one is going to have a higher chemical shift? The one in the blue circle or the one in the red circle? Does anybody have a guess? Which one would be the higher chemical shift? Which one would be the C protons? Would it be the ones in the blue circle or the red circle? I'd say it's the ones in the blue circle, because the electron withdrawing effect of an alcohol, that's right, Aaron, is very strong, right? So this means this is going to be C. I'll use the blue pen. This is going to be C, this is going to be B, and then all 5 of these would be A. Okay, all 5 of them. You can't distinguish between them because it just gives you a multiplet. So there you go. We were able to determine the structure of this compound from the proton NMR spectrum only. So when we do carbon-13, excuse me, remember, carbon-13 is only about 1%. It's about 1.1% abundant. And so proton is by far the most abundant isotope. And that's why proton NMR signals are generally strong. But like I said, carbon-13 is only about 1% of carbon. And so you need a sensitive receiver coil in your magnet, or you need to have a concentrated sample, one or the other. The easiest thing to do is to just have a lot of your compound, right? To have a very concentrated sample, then you have a lot more carbon-13 atoms and you can get a good spectrum. But like we just saw today, in proton, we looked at chemical shift, splitting, meaning the n+1 rule, and then we looked at integration. However, we don't look at splitting for carbon-13. We just look at the number of signals and chemical shifts. So I'm going to put here, no splitting. No splitting, like that. So there is such thing as carbon and hydrogen splitting. It does happen, and sometimes we do look at it. Okay, rarely. So I'm going to put here no splitting. We'll put here usually. There are exceptions where we are interested in the splitting, But if you're wondering, like, why wouldn't you be interested in it? The reason why is that it's usually very complex. Okay, it's so complex that it's very difficult to read. Like you can't even make it out. So if it's something that you can't make out, I mean, it's not useful for us as scientists. We need information we can use. And so what we do is we run what's called a decoupled spectrum, and that prevents any splitting between the carbon-13 atoms and the protons. And so all we get are singlets. Every single carbon comes up as a singlet. Again, there is such thing as doing a coupled spectrum, and I'll probably show you that tomorrow. So don't worry about it today. So it says here that compared to proton, carbon requires a different frequency to cause the nuclei to resonate. So instead of going from about 0 to 12 parts per million, compared to TMS, when you run carbon-13, the spectrum goes from 0 to 220 parts per million. So it's a much broader range. And like I said, every singlet represents a unique type of carbon. So if two carbons are chemically equivalent, they're going to resonate at the same frequency. You don't get two peaks. So again, planes, axes of symmetry can cause carbons to be identical, and they're going to resonate with the same frequency. And so they're going to have the same chemical shift. So if you look at these three compounds here, now remember, we're not talking about proton. We've moved on from proton. We're talking about carbon-13. And so if we're thinking about carbon-13, if you look at the compound on the left, you see a total of what? 1, 2, 3, 4 different signals. If you look at the one in the middle, you have 5 signals. And if you look at the one on the far right, you have 3 signals. So symmetry works the same way. Now, the table that I'm going to give you for the quiz is not nearly as busy as this one. It doesn't have nearly the amount of information. But this is the kind of the idea of where chemical shifts are for carbon. So you see that if you have an alkane, alkanes have the lowest chemical shifts, from 0 to 50, it looks like, or maybe a little bit above 0. Carbons that are bound to a halogen can go anywhere from, you see 0 to above 60 a little bit. Bonds to nitrogen fall in this range here. It looks like about, high 50s to, high 30s to 50, something like that. Bonds to oxygen are going to be higher, right? So you see bonds to oxygen go from like 50 to 80. Triple bonds are in the 60 to 90 neighborhood. This is where it gets more interesting. Double bonds have a huge range from 100 to 150. And aromatics, you see those go higher from 110 to 170. And then the highest chemical shifts you see in the carbon spectrum are going to be anything with a carbonyl. So if it's in carboxylic acid, ester, or amide, those are a little bit lower. They're from 160 to somewhere in the middle here. So maybe around, 190. And then above 190, that's going to be your ketones and aldehydes. All right. So those are generally, where you find the chemical shifts. This is a table that's found in your textbook. So it kind of starts out with alkanes, whether it's attached, these are all attached to sp3 hybridized carbons, but depending on the number of substituents, the chemical shift again can range from 10 to 60. If it's attached to an iodine, it's 0 to 40. Bromine is 25 to 65. To a nitrogen, it's 40 to 60. You see chlorine is here. Oxygens, alkynyls, like I said, 60 to 90 in that range. Alkenyl, so again, 100 to 150. Aromatic, 110 to 170. Esters, amides, carboxylic acids are a little bit lower. The kings of the castle would be an aldehyde or a ketone that have really high chemical shifts. Now, see, I went over those pretty quickly, but the best way to master it is to try it. But let's start out by taking a look at these two compounds and figuring out how many signals we would see in a carbon-13 NMR spectrum. So if I draw the first compound like this, okay, maybe like that. Could anybody tell me how many signals you would see for this compound in the carbon NMR? How many signals would you see? So for this one, let's see here. There is definitely an axis of symmetry through the molecule like this. So I got 5. So we would have these two methyls are chemically equivalent. So that's 1. Then we have this quaternary carbon, which counts. So that's 1, 2, 3, for these two methylenes, 4 for this guy here, and then 5 for the last one, for the last methylene. Come on. So for this guy, we would see a total of 5 signals. All right. Does that make sense now that you see it? Okay, cool. What about the last one, or the one on the bottom? So I'll just redraw the compound here. So what if we draw it like this? So if we put the aromatic ring like this, and then we put CH2 and CH3. Anybody figure out how many signals you would see for this compound? Thanks, Rubio. Exactly. You'd see 6, wouldn't you? You'd see 1, 2, 3, 4 for these guys, 4. Then you'd see 5 for these guys here. And then you would see 1 here. And that's a total of 6. Here you go. Great. Awesome work, you guys. Not an easy question. So 6 signals. Great. Awesome. So before we finish up the chapter, there's one last type of spectroscopy that we talk about, and it's called a depth spectrum. Depth stands for distortionless enhancement by polarization transfer. Don't worry, you don't need to know the acronym, okay? All you need to know is the 2 experiments, which are a depth 90 and a depth 135. So let's think about this very carefully. You're going to see how depth is like the coolest thing. I mean, sliced bread is pretty great, but I'm thinking depth might even be better. Okay, so if we go all the way back here to the beginning, okay, and you guys just figured out how many signals you get. So in our carbon-13, when you run a regular old decoupled spectrum, every unique carbon shows a signal in the spectrum. But when you look at the carbon, it doesn't have, there's no coupling. So you're like, well, which one is which? I guess if it's got a really high chemical shift, you might be able to say, well, that's a carbonyl or something. But check this out. Whoever invented the depth experiments, I would love to party with this person because I think they're like the coolest person ever. So the 2 experiments are this. Okay, so here's what you would do, my friends. Pay very close attention. You go to the lab. You take your organic compound. You run a carbon-13 spectrum, just a regular decoupled spectrum. You see, like, let's say 7 signals in the carbon NMR. So you're like, okay, great. There's 7 unique types of carbons in my molecule. Whoop-de-doo. Okay. Then you say, well, what are the types of carbons that I can have? I can have a carbon with 3 hydrogens attached to it. I can have a carbon with 2 hydrogens attached to it. I can have a carbon with 1 hydrogen attached to it, or I can have a carbon with no hydrogens attached to it. Wouldn't it be great if you could look at each one of the signals in your decoupled spectrum and you could identify them as methyls, methylenes, methynes, or carbons that are quaternary, that have no hydrogens? And by using these 2 experiments, you can do it. So here's the answer. What you do is you run this experiment. It's called a depth 90. It's literally a click of the mouse on your NMR spectrometer. And you rerun the spectrum, but the only thing that shows up are the methynes. So then you can go back to your initial spectrum and you say, well, I know where all the methynes are, okay? But then you don't know where the methyls, methylenes, and quaternary carbons are. You can't identify them. So then you run another experiment, which is called a depth 135, which is like the greatest thing in the universe. And what it does is all the methyls and the methynes are going to be pointing up in your spectrum. And get this, you're going to laugh, but the methylenes are pointing down in the spectrum. You're like, really? Yeah, they're pointing down. So now you can go back and you can say, okay, well, I knew where the methynes were. So now everything that's positive means I can identify all the methyl groups, right? Everything that's pointing down is a methylene. And whichever peaks from my initial spectrum didn't even show up in any of these, I know that those are the quaternary carbons. So by running 3 experiments, you're able to identify all 4 types of carbons. So again, in the broadband decoupled, just a regular spectrum, you see all the signals. Then you do a depth 90, you identify all the methynes. Then when you run a depth 135, you can identify all the methylenes because they're pointing down. You can identify all the methyls because it's anything that's positive that didn't show up in your depth 90, and anything that didn't show up in either of these must be your quaternary carbons. As we say in French, c'est pas beautiful, ça? Give me a thumbs up if you're with me on the idea, at least. If you're like, all I have to do is run those 3 experiments, which are just a click of the mouse, and it's going to pulse it in a different way, and it gives me that information. I know what you're thinking. Can you give me that information for every single spectrum? The answer is no. Okay. Sometimes we give it, sometimes we don't, but it's a pretty wonderful thing. So let's see if we can use it to our advantage here. Okay. This question 50.28 says determine the structure of a compound with this molecular formula. So I'll just do it quickly. We've got an HDI equal to 1 for this compound. It gives you the following broadband decoupled 135 carbon 13. And it says here the depth 90 has no signals. So let's go back. The depth 90 has no signals. So that means there's no methynes. Okay. So we can say based off of the depth 90, we can say no methynes. There are none of these in the molecule. Okay, so now if we look at the depth 135, we know that anything that's pointing up must be a CH3. So this is a methyl group. This one here must be a methyl group, right? Because you see, these are the same thing, right? These and these, okay? But then in the depth 135, it gives you the same signals, but you see that these ones are pointing down. So these must be, this must be a CH2, and this must be a CH2. Could anybody identify this signal way the hell up here? If it's over 200, if it's around 210, what do we know about that carbon? What's attached to that carbon? If it's all the heck the way up at 210. If you don't remember, let's go back the table. If it's all the way up at 210, it must be some kind of what? Aldehyde or ketone. All right, give me a thumbs up if you're with me on that. Okay, it's got to be an aldehyde or a ketone. Okay, well, I can tell you it's not an aldehyde, right? We can tell it's not an aldehyde. How do we know that? Because there's no CH in here, right? So that means it must be a ketone. It's got to be a ketone. So your HDI is in here, is in the double bond. Okay, so that's this. All right. So what are your pieces? So now let's, if you guys like puzzles, let me give you a puzzle. You've got a carbonyl. Okay, you've got this piece. You've got 2 CH2s. So CH2 and CH2. And then you've got 2 CH3s. So now you have to assemble this somehow to give you some kind of structure. Okay, that's what you've got to do. So what if we tried something like this? What if we put the carbonyl here and we put a methylene like this, another one like this, okay? And then if we put a methyl group over here like that, and then what if we put the last methyl, I'll just write it like this, CH3. Okay, like that. There you go. Does that look reasonable to everybody? Something like that? I kind of made a mistake. I didn't want to show you this compound first because this is actually the correct compound. This is right. What I should have done was this. If I was a more astute instructor, I would have drawn this and then said, what if I have CH2 and then CH2 and then CH3 and CH3. So I'll ask the question a different way. You know, make lemons out of lemonade here. Make lemonade out of lemons. Jeepers, I need another coffee. Could anybody tell me why it's not this compound, the one in the green box? Why is that wrong? If somebody had proposed that, why would, like Mr. Dion, why would it be incorrect? Yes, exactly. 3 signals, right? Exactly. Why must this be the correct one, Isaac? Because it's got 5 signals, right? 5 unique signals. Awesome. Here we go. So now, if we want to annotate the spectrum, what we do is this. We always start on the far right, and we use the alphabet. So we use A, B, C, D, E. Obviously, this is the E carbon, okay? Now, between the 2 methyl groups, the one that's going to be more deshielded, having the higher chemical shift, is the one that's going to be next to the carbonyl. So this would be C, this would be A, oops, not D, A. And then between the two methylenes, the two CH2s, the D one would be the one closer to the carbonyl, and then the B one would be the one farther away from it. So there you go. That's it, my friends. Is that cool or what? Is the depth experiment awesome or what? It was like one of the coolest experiments ever created, I think. Again, I want to hang out with that person. I'm going to leave the part about MRI as an FYI. I figure there's enough content already in here, but you could take a look at the MRI section. Anyhow, there you go. So that covers all the content for the chapter on proton and carbon NMR spectroscopy. So just give me a second here. We'll take a break in our recording here.